Chapter 18, Section 6 adds in a few new summing amplifier circuits. Now, if you recall from Chapter 16, we looked at the simple summing amplifier circuit, and in this case we could multiply two input voltages by a different value and add them together. And it worked because the input circuits created a summing node that added current together that went through the feedback resistor. So you ended up with an output that was equal to the gain of the first voltage plus the gain of the second voltage multiplied by what's coming in. And the gain in each case was the minus RF over the appropriate resistor. So for voltage 1 it was minus RF over R1, and for voltage number 2 it was minus RF over R2. So that would be your output voltage. It would be the individual gains multiplied by the input voltages, and then you add them together. Now this works pretty good if you want negative voltages all the time, but what if you want an equation that's something like Vout equals 3 times V1 minus 4 times V2, where the multiplication factor or the gain factor is a positive in one case and a negative in the other case. What do you do in that situation? So the easiest way to get whatever kind of equation you want is simply to put two op amps one after the other. So over here on the second half here, you can see that this one here is a summing amplifier, and it's preceded by an inverting amplifier. So what we do for the stuff that we want to add in is we apply those voltages to the first op amp, and for the things that we want to subtract, we put onto the second op amp here. So let me give you an example. Let me add in a few more inputs. So let's go down here. I'll add in V4, and I'm going to add another input over here. We're going to make this V3. So let's say I want an equation that is 3 times V1 plus 4 times V3 minus 2 times V2 minus 6 times V4. Let's say I want that equation applied to this input. So let's look at the positive ones, 3 times V1 and 4 times V3. I pick a common denominator, make this 12K, make this 4K and 3K. That gives me 3 times V1 plus 4 times V3. And I've written down the final positive values. They're actually negative gain factors at that point. And I can use the same value again. If I put 12K here, for R1 I could have 6K. So 12 over 6 is 2. And then 12 over 2K is minus 6. So these values here would give me minus 2V2 minus 6 times V1. And then in order to get this first part here, in order to get this amplified by minus 1, I would make this guy here also 12K. So there you have it. Vout equals 3 times V1 plus 4 times V3 minus 2 times V2 minus 6 times V4. So 4 input voltages, 2 of them multiplied by negative gain factor, 2 of them multiplied by a positive gain factor. All the gain factors are different. So figure 18-22 shows you a circuit that can amplify multiple inputs by both positive and negative gain values, and it does it in a single op amp stage. And this is an impressive circuit. The problem with this circuit is that the formulas required to find the output voltage are equally impressive. Now, if I gave you the resistor values for this circuit, I think that you could spit out the correct formula for Vout. But the problem is, if I gave you the formula and asked you to give me the required resistor values to achieve a specific formula, I think that would be a big challenge that would take a couple of days of effort to figure out. And I don't think that's worth it. So given the choice, I would go back to figure 18-21 and just do a two-stage amplifier. Figure 18-23 is an application circuit for summing amplifiers. And what they're doing here is they're finding the average value of 3 input voltages. And they do this by making the feedback resistor R and each of the input resistors equal to 3R. And so what this means is that the gain for all 3 inputs is going to be minus R over 3R, which is 1/3. So V out is going to be equal to V1 over 3 minus V2 over 3 minus V3 over 3. Divide each one by 3 and add them up. That gives you an average of the 3 voltages. Another useful summing amplifier circuit is the binary weighted digital to analog converter. So D to A stands for digital to analog, and what this circuit does is it will convert digital values on this side, and there are 4 of them, V3 to V0, and it'll convert that to a single analog voltage on this side. So here we have 4-bit inputs, so the digital values can be 0 to 15 on the input, and in hex we'd say that's 0 to F. So you can have something like 0, 1, 0, 1 applied to the input. And this would be 5 over 16. So we can develop a formula for V out by looking at the resistor values. So for V3, it's going to be R over R. So V out is going to be equal to minus R over R times V3, which is just going to be V3 over 1. Now for V2, it's going to be R over 2R, which is going to result in minus V2 over 2. And then for V1, we have 4R, so it's minus V1 over 4. And then finally, for V0, it's 8R, so it's going to be minus V0 over 8. So what they've done is they've multiplied the resistors by 2 every time they add on a voltage, and then that means that each subsequent voltage is divided by 2. So we have a V out equals minus V3 over 1 minus V2 over 2 minus V1 over 4 minus V0 over 8. So let's put our digital value of 0, 1, 0, 1 into this formula and see what kind of output voltage we get. So V3 is 0 volts, so that would be minus 0 over 1 minus 1 volt for V2, which is a half, 0 volts for V1, so 0 over 4, and then minus 1 over 8 for V0. So that would be minus 0.5 minus 0.125. We would get an output voltage of 0.625 volts. So for each digital value, we would get a corresponding output value, which is a weighted sum of what's coming in. So let's say we put in 0, 0, 0, 0. This bit is worth 1. This bit is worth a half. This is worth a quarter, and this is worth an eighth. So for 0, 0, 0, 0, we'd get an analog voltage of 0 out. Was 0, 0, 0, 1, we'd get 0.125 out. That would be this bit over here. If we got a 0, 0, 1, 0, that would be 1 over 4, so we'd get 0.25 volts out. And of course these are negative voltages, so 0, 0, 1, 1 would be a quarter volt plus an eighth of a volt, so we would get minus 0.375 volts out. So you can see that as we go through this table, we are finding that for each digital input, we have a corresponding analog output voltage. What's the biggest voltage we would get? So the biggest one that we would get would be 1111, which would be 1 volt minus a half a volt minus a quarter volt minus an eighth of a volt. That's 1.5, 0.75 minus 1.875 volts. So we'd get a little bit under 2 volts. So this is a digital to analog conversion. So the problem with the weighted sum digital to analog converter is that you need precision resistors in values of 1, half, quarter, eighths, all the way up to however many bits you want to have. So another way that you can do this is what's called an R2r ladder network, where you can create the same ratios with only 2 resistor values, and that's shown here. So what we have is 2 resistor values. We have 20K and 10K. And when they're arranged in a ladder network, so here we can see all of the rungs on the ladder are 20Ks and all of the sides of the ladder are 10Ks, we get a voltage divider happening that gives us a voltage at this point right here, which is half of D3 and a quarter of D2 and an eighth of D1 and a 16th of D0. So here's our input switches here from D0 to D3, and when they're switched back and forth between a ground, a 0 logic level, and a 5 volt level. So the final output for this circuit will be V out will be equal to D3 over 2 minus D2 over 4 minus D1 over 8 minus D0 over 16. So it achieves the same binary weighted sum as the previous circuit. It just does it with less resistor value. If you want more information on the R2R D to A converter, that can be found in Appendix D, which shows you how that works.